Welcome to Data Structures and Algorithms class. So data structures is one of the fundamental building blocks of computer science. And then paired with algorithms, this is how we can design efficient programs. Now, what does efficient even mean? This is what we're going to learn, as the main objective of data structures and algorithms is to solve problems in an efficient manner. Now, solving problems in an efficient manner, it doesn't even have to be about programming. You actually use some sort of data structure and algorithms on a day-to-day basis. Like, for example, when you need to find a word in the dictionary, how do you do it? I mean, there's one way you can do it. It's a very inefficient way of doing it. You can read it line by line and page by page before finding the word you're seeking. Like if you want to find the word garage and you start from the first page with a bunch of words starting with A. But that would be inefficient, right? So what would most people do? Well, you would use the index to find the appropriate first letter to jump ahead and then search for the word. So basically, your dictionary is actually like a data structure because it stores, organizes, and groups these words together by sorting them alphabetically and also having these A, B, C, D, E indexes. And basically, the words is the same thing as data. And then the way you search for the word, the action of searching, this is actually your algorithm. Now, to show you the importance of a data structure, would the method of finding the word you want work if the dictionary was not alphabetically sorted? No, it wouldn't, because the whole point is that the dictionary is sorted in alphabetical order, which is why you can use the indices. And then also why you can kind of flip through several pages knowing that the word won't be there. However, if the words are sorted randomly, then there is no way of finding a word except for reading it line by line and page by page. But that would be extremely inefficient. So which is why the data structure, aka the dictionary, is important. So that's why to design efficient algorithms, you often need the appropriate data structures. Let's look at more examples in our day-to-day life where organizing data helps us do things more efficiently. For example, index folders, they help us retrieve documents more efficiently by putting similar documents together in the same index. In computer science, there's a data structure called hash map that does something similar. For example, if I had, let's say, text documents on 3 and medical documents on 6, then if I want to access them, I could access them real quick by just using these index. A corporate structure in a company where you have managers and their reports, and then also these reports are also managers of more reports, this is basically a data structure. This allows the company to give orders more efficiently. So instead of having Mark Zuckerberg here talk to everyone in the company, to delegate work to everyone, what Mark can do is he can delegate a huge chunk of his work to his direct report, which in here he only has 3. Once you give a big chunk to all these 3 reports, these reports themselves can break down that problem or that work to their own reports. And then until all the way to like the menial employees that do not manage anyone, like me. For example, we should draw a few more nodes until we get to me. There we go. Right? So then by then, I only have a small piece of work to do. And this also allows us to know exactly what your relationship is with different people on the organizational structure. In computer science, we have something called a tree structure, which is kind of the same thing. And we also have maps, they usually have coordinates. In this example, we have the latitude and longitude, and you could see that each square is represented by a number and a letter. So these are basically like coordinates. So this is useful so that it allows you to locate, for example, a lake or a house, a church with a longitude and latitude. For example, 3E, imagine 3E, that is where the lake is. And then, for example, this island is on 1E. So this allows people to retrieve certain areas or at least certain monuments quickly. In computer science, we have matrices to represent a 2-dimensional plane. So data is everywhere. Your pictures in Google Photos, the text on a website, your friends on Facebook, this is all data. And the way we organize this data matters so we can deal with it in an efficient manner. Being able to deal with it efficiently means the programs and software will run a lot faster. And the thing is, different types of data structures are suited for different kinds of applications. You can't just use one data structure for everything. And some of them are highly specialized for specific tasks. So the definition of a data structure formally is a data structure is a format to help organize, manage, and store data in your program so it can be accessed and modified efficiently. Now, data structures, the name can be a little bit confusing sometimes. When people talk about data structures, they might be referring to two different things. Either they're talking about abstract data type, or they're talking about the actual data structure that is behind the data type, which is the implementation. For example of data types, we have lists, stack, queues, tree, graphs, and many more. So then these are abstract data types, and then the implementation, for example, for a list, it could be arrays, or for example, a linked list. And then same goes for stacks. It can be implemented with arrays or linked lists. So then these are the data structures and these are the abstract data types. Now here's a drawing that makes it easy to understand what abstract data types are. So this is an abstract data type, all right? Like for example, the list. And then what an abstract data type has are operations. Operations basically define what we can do with the abstract data type. Like for example, in our list, we can put multiple elements in the list. We can modify a list given an index. We can remove elements based on the index. I think that's pretty much it. Yeah. So that's what a list is. And then those are the operations that a user can do. A user does not know what algorithms is inside the abstract data type, and it does not know what the data structures are. It does not care about the implementation. Implementation of an abstract data type uses algorithms and data structures. In this course, we will learn about many abstract data types, and when we learn about each abstract data type, we usually care about a few things. We care about what are the operation, or we could think of it as an interface. What kind of interface does this abstract data type have? What can the user do with this abstract data type? And then we will go deeper and learn about the implementation. And the implementation, we learn about which data structure can we use and what kind of algorithms can we use on these data structure so that we can serve the users and do these operations for them, right? And then given that there are different algorithms and data structures that we can use for the same abstract data type, then we're going to care about the cost. And then the cost is in terms of memory, meaning how much space does it take? And also in terms of how fast the algorithm is. Is it a quick operation because the implementation has a fast algorithm? But does it take a lot of memory because it requires you to store a lot of different data structures? And then also, why is this abstract data type useful? We're going to learn about that too. So to summarize, we care about the operations, the implementation, and then the cost, time, and space. So to do something more fun, let's use a real life example of what a abstract data type can be like, an example. So let's think about a washer dryer machine. So I'm a user, and let's say that this abstract data type is a washer dryer machine. So washer, dryer. All right. What are its operations? What is its interface? Well, I know that a washer dryer can do two things. Maybe three things. You can put clothes in, and then you could wash them, and then you can also dry them. So me as a user, I don't really care how this washer dryer works or how it's implemented. I only care that I can put my clothes in, I can wash them, and I could dry them, right? So these are the operations. All right. So instead of data structure, what is it? What is the method? What is the method of washing these clothes? Well, there's different ways. Let's say the first one uses like the algorithm. It uses water it uses water and soap, right? This can be the implementation. I don't know that, but we can use water and soap, and then we'll spin it. This is the algorithm. We'll spin the clothes inside and we'll add some water and soap to clean it. And then that's basically how this washer dryer works. That's the implementation. However, the thing is, we can have another washer and dryer that is different, that is totally different. This washer dryer uses petroleum solvent, and then what it does is it dry cleans my clothes, right? So now this washer and dryer is a little bit different, but in the end, for me as a user, it's the same thing. I just put clothes in, I wash them, and then I could dry them. And then there you go. This washer and dryer has a different implementation because it dry cleans by using petroleum solvent to clean my clothes. So it doesn't use water, nor does it spin, right? And then we can argue memory. We can say like, oh yeah, maybe it uses more electricity or something, or maybe the space is really big, right? And that's how you can compare washer and dryer. And then time also, maybe dry cleaning takes a lot longer than spinning it with water. So yeah, so that's pretty much what abstract data types mean. So you can kind of think of abstract data type as something that logical. So to formally define abstract data type, it's a mathematical or logical model where you specify its behavior from the point of view of the user. It defines the data it can hold and what operations you can do to it, but it abstracts the implementation away. So it's a theoretical concept, right? So it's theoretical. And then for data structure, it's the actual implementation behind the abstract data type. So that's it for this video. And in the next video, I'll be talking about our first abstract data type, the list. All right, I'll see you next time.